As mentioned, and as the title says, I'm gonna talk about applications and our attempts to get some kind of explanation about how AI works in the field of atomistic modeling. So before I start, I always like to start by showing the faces of the people who do the work, the people who pay the bills, and yeah, our social. Now we are migrating to Mastodon, but whatever. Getting actually to the subject matter, I want to, since this is a very heterogeneous audience with people working in very different domains, I wanted to clarify what is the domain in which we are trying to do this stuff, and a little bit what is also our background, what we were doing before machine learning was a thing. And so the general idea of what we want to do is to model matter at the atomic scale. And the idea of modeling matter at the atomic scale is that this allows you basically to tap into fundamental physical laws and build a hierarchy, multi-scale, very traditional yet fashionable way of describing this idea, but you start from the foundations and then you build a hierarchy of models that allow you eventually to make predictions about the behavior of a material in a realistic situation or the behavior of a molecule in a therapeutical setting. So the notion is that since we start from fundamental laws of physics, we can be predictive. So we don't rely on experimental observations. We can make predictions about a molecule or a material that doesn't even exist yet. That's the general idea. So this is very nice, but it's also very difficult. If you try to do this transfer process from fundamental physical laws to macroscopic phenomena, you have to essentially deal with the fact that nature is both extremely finely tuned and extremely prone to exhibiting emergent collective behaviors. This basically means that on one hand, you need to be extremely accurate in the approximation that you apply, for example, to solve the electronic structure problem, but at the same time, it's not enough to make a single prediction for a highly idealized structure of a molecule in the gas phase. You need to put the molecule in a solvent, you need to study the interaction of that molecule with others, you need to study phase transitions that can arise even from very simple interactions. And so the result of this is that this is a program that has progressed a lot, but it's horribly expensive from a computational point of view. So the idea over the past few years has been to use machine learning to basically sidestep some of the computational bottlenecks in this process. And I think it's very important to clarify in which way we are trying to do this, because usually, not always, but most of the time when you speak to the general public or to a company, for instance, about machine learning, the idea that people have in mind is one of performing an end-to-end prediction. I take the simplest possible description of a chemical compound, its composition, and I want to predict what will happen when this compound is put into the human body. So what we try to do is something different and something which still relies on the same notion of doing a bottom-up model in which you start from fundamental physical laws, you see where the atoms are, how they interact, sum over statistical fluctuations, and eventually you get a mechanistical insight into how the problem can be solved and into how the molecule works. So from a certain point of view, by construction, we have an insightful approach because we don't apply machine learning in a completely black box fashion, but we use it to essentially sidestep some of the computational bottlenecks of these very, analytical and mechanistical workflow. So typically the main computational bottleneck in all of these, well, not everywhere, but at least in a lot of the things that we work on, is actually the solution of the quantum mechanical problem. So what you want to do is to apply some type of approximation of a Schrödinger equation to start from the coordinates of the atoms and predict, for example, the interatomic potential that tells you whether a structure is stable or not. but also to predict a lot of other observables that can be linked to experiments and that can be linked to the behavior of a material or a molecule in a useful context. So the idea is that rather than using quantum mechanics to do this, or better, after having done this with quantum mechanics on a certain number of reference structures, we use a surrogate model that is based on some kind of data-driven technique. So in order to try also and gain insight not only through the application of these models built with machine learning and applied in the context of molecular dynamics, sampling, or whatever, but also to gain insights from the model itself, I think that a very important first step is understanding your model. And this is a theme that has been quite recurring, understanding what are the physical priors that you're including into the model, how is the model restricting the space of possible solutions. So we have been working a lot toward this goal of perhaps it's a little bit pompous, but we call this a unified theory of atomistic machine learning. So try to take the many different practical solutions that have been developed over the past 10 or 15 years and try to systematize them and try in this way to understand what are the main ingredients, essentially. And so if you look from a mathematical perspective at how the problem that we are trying to solve can be formulated, essentially what we are working with is a decorated point cloud. So we have a set of Cartesian coordinates of atoms, and each atom has a chemical nature. So basically, this is a three-dimensional point cloud, and one way of looking at this is basically to look at this as a problem of describing three-dimensional point clouds. Another point of view on the same problem, which is actually one which is typically used, people coming from cheminformatics, is to regard molecules as graphs. And here I want to stress, when I say graphs, I don't mean just discrete connectivity type of graphs, but these are more geometric graphs in which basically the edges are decorated with information on the distance or the geometric relationship of different atoms. Okay, so there is a graph, the structure of a graph, but in addition, there is also geometric information. So the point is that what we are trying to do here is to make a link between this point cloud and a physical property that corresponds to a property of a molecule. And this means that the mapping between the point cloud and the target has to fulfill some very fundamental physical constraints. And therefore, if we use some type of featureization for our structure, the mapping between the structure and the features should be consistent with these fundamental physical requirements, because otherwise, in no way, a model that we build then on these features will be able to fulfill these requirements. So for starters, and this sounds a very basic requirement, but it's actually tricky, we require this mapping to be complete. So we want that if two structures are different, they should be mapped to features that are different, because otherwise nothing that you do will be able then to predict the different properties. And what makes this not so trivial is that simultaneously we also require this mapping to be symmetry adapted or symmetry preserving. Basically, if two molecules are have different coordinates but correspond to a rigid rotation, then it's very useful if the features are the same, because then the properties will be the same without you having to do any work in the structure of the model. Yes?
And if you have a structure that has two of the same atom, which could be flipped between the two of them,
yes.
Are they regarded the same or different?
They are the same. So permutation symmetry is another fundamental symmetry that, permutation between atoms of the same type is also something that it's actually perhaps even more important than rotational symmetry. We want the mapping to be smooth because nature is smooth at the atomic scale. And something that is perhaps a little bit less obvious, but it's actually very useful and important, usually we build models that have an additive nature, that have an additive structure. So we build the description of a molecule and the property of a molecule as a sum of atom-centered, of atom-centered contributions. So this doesn't mean that, so here, for instance, the energy of a molecule will typically be written as a sum of terms that are associated with individual atoms. And this is not atoms in isolation, but is atoms together with their local environment, okay? So this actually, making this kind of ansatz for the target implies also, depending on the type of, for instance, you build a linear model, this also means that the features for your structure should be the sum of the features for the environments. If you build a kernel model, these ansatz require that the kernel between structures is the sum of the kernels between environments. So basically, these additive ansatz on the targets translates into an additive ansatz on the structure of the models and the structure of the representation. Now, the reason why, to understand why this is useful and why this is important, is that it basically gives the models a divide and conquer type of nature. So you can essentially train your model on simple systems and then take them apart and put the pieces back together into something which is more complex and more interesting. And so this is typically how you can get to describe emergent behavior starting from training on relatively simple systems. So even though there are all of these requirements that in principle constrain the space, the design space of possible models, people have been incredibly creative. And if you look at the past 10 or 15 years, you probably will find at least a couple of hundred of alternative frameworks to do this mapping of a chemical structure into a set of features. And this is from, well, now 2 years ago, time really flies, so this is like a previous geologic era in machine learning time, but this is a small selection of the frameworks, the ones in gray that have been proposed. And we tried to classify them based on the way symmetries are incorporated starting from Cartesian coordinates. And in doing this exercise, we realized that actually most of these frameworks are really computing the same thing. And they are just essentially computing the same thing using different routes to get to the same result, or doing actually fairly small variations on a team, essentially projecting on different finite bases the same abstract objects. And so we have been able to build a kind of a systematic construction that generates some abstract objects, abstract features that once projected on a specific basis generate any of these alternative frameworks. And the idea goes like this. Okay, so you start from the Cartesian coordinates of the atoms. Easy to understand. I say where each atom is and what each atom is. Not symmetric at all. If I swap these two rows in the matrix, it's the same structure, but it's a different set of numbers. So of course, then the model would have to learn that the properties have not changed. So the first step is to map this list of numbers into a field, a density field. Essentially, we put not a finite support, but a localized function on top of each atom. And this basically is a lossy operation because the atoms typically never overlap. So you can still very precisely reconstruct where the atoms are, but you cannot tell whether this is atom 1 or atom 76. So now we have a permutation invariance built in, but we don't have even a translational invariance. Because if I change the origin, this becomes a different function of 3 coordinates. And I should also stress that we encode the information on the nature of the atoms by using different channels for the density. This will become important later. And then, I mean, this is a long story. I could spend 1 hour discussing the details of these. But basically, the idea is that then, starting from here, we sit on each atom. So we basically we refer this density to different atomic centers, and in this way we make it translationally invariant. And then we compute symmetrized correlations of this density. Basically, we compute this neighbor density at different points, and we symmetrize by rotating all of the densities at the same time. So this basically is a way to build descriptors that are invariant to rotations because they are averaged over rotations. And depending on how many densities you correlate, you bring in more and more information on the relative position of the atoms until eventually, or at least this is the idea, you get to a complete description. And actually it turns out that not only you do get in the limit in which you take as many densities as you have neighbors around an atom, you get to a complete linear basis to expand any symmetric function of the atomic coordinates, but also for those of you who are a little bit familiar with atomistic modeling, you recover some very traditional schemes to describe atomistic systems. If you use these density correlations in a linear model, what you recover is a hierarchy of body order terms. So basically, if you take a density correlation that considers just one neighbor and you build a linear model, you build a pair potential. So energy of your structure is a sum of interactions between pairs of atoms, like electrostatic interaction or dispersion. If you take a two-neighbor correlation, you get three body potentials, and so on and so forth. And of course, then, if you build a nonlinear function on these features, everything gets much more complicated, and I will return to that. I want to stress, however, also that what is, at least in my opinion, of course, probably I shouldn't be the one to judge this, but what I really like about this framework is that it's very easy to extend it and generalize it. So, for example, if your target is not a scalar, but is, for example, a vector or a tensor, and so you want to build a model that is not invariant, but is equivariant to SO3 operations, it's very easy to generalize this scheme. All that you need to do is incorporate essentially an analyzer, a spherical harmonic, that basically extracts the component of the density correlation that has the character of an irreducible representation of O3. So basically that's the idea, and it's actually, I mean, it's cumbersome, the algebra, but it's actually relatively easy to do. And something I will try also to briefly mention is that we also generalize these in a scheme that allows to also go beyond a fully local description of the system by essentially constructing a field that incorporates information on the long range structure of the system. I don't know if I will have time to get into the details of this. Another aspect that I want to stress is that actually there is a lot of connection between this approach that is atom-centered with a lot of very recent deep learning approaches, and in particular everything that is an equivariant model is essentially the same thing as this. Because when you build equivariant models, you are constrained in the operations that you can do by the need of remaining equivariant with respect to the action of O3. And therefore, the only thing that you can do really to make your model more complex is to build SO3 symmetric products that are basically Clebsch-Gordon summations. And because of these, eventually you can show that at least in the appropriate limit, all of these equivariant models are equivalent to building features that are not centered on an individual atom, but that combine information on densities centered on different atoms. And basically, the contraction over the correlations of neighboring atoms is what builds the structure of a message passing architecture. So, the idea in the reason why we're doing this, you might ask yourself, okay, why are you doing this? Well, the reason why we're doing this is that, okay, my impression at least is that a lot of the models that are appearing in this field are a little bit like pre-mixed drinks. So many choices have been made for you. The descriptor, the regression, the initialization, the data set, and you get something that works, no? If you like it. But it's, to me, it's not fully satisfactory because I don't understand how these different ingredients come together to make something that is pleasant to drink. So instead, what we are trying to do is a sort of decompose these into the different ingredients with the end goal of allowing everybody to basically mix their own. And one of an example on how this decomposition into the fundamental building blocks of a model allows you also to extract some insights into the way a model works is that basically you can rather than just comparing two models that are finite products in which 100 different choices have been made, you can just change one ingredient at a time. So here, for example, I am comparing the learning curves for models that are built with linear regression. So the model is very simple. And in one case, I'm using features that are restricted to two neighbor correlations. And another case, I'm using features that are restricted to three neighbor correlations, all centered around the same atom. And you see that there is a certain improvement in the accuracy because, of course, I have now a model that has more flexibility and it saturates later. So there is one thing that we learn from this is that the structure property relationship in this system cannot be fully described by two body correlations. You need higher body order. It's very clear from the saturation of the learning curve. Something which I find extremely interesting, however, here is the difference between the green and the blue curve. Because both the green and the blue curve involve correlations between three atoms. But in the case of the green curve, all the three atoms are centered around the same one. And in the case of the blue curve, I'm basically looking at the correlation between one atom and one of its neighbors and the neighbors of one other of its neighbors. Okay, so this is a message passing structure, and this leads to a massive improvement of accuracy, which is very strange because in the complete basis set limit, these two descriptions provide exactly the same descriptive power. So what this means is that at least for this family of problems, using a message passing construct gives you a much more efficient discretization of your correlations. And essentially, those of you who are a bit of familiarity with chemical problems, the reason why this is the case is that this is a data set in which I have a carbon atom in the center and 4 hydrogen atoms completely randomly distributed up to 4 angstrom from the central atom. So what is happening here is that hydrogen atoms that are very far from the carbon can form a bond between them. And if I only look at these from the vantage point of the carbon, I need to try and describe, basically with angular information, what is the distance between these two atoms, which is very, very hard. I need incredibly high resolution. And instead, the message passing construct allows me to basically look at the hydrogen from the vantage point of its neighboring hydrogen, which is much, much easier. Okay? And so the fact that I can do this interpretation is due to the fact that I'm not just taking a pre-mixed model, but I can just change this ingredient without changing everything else. And another interesting observation is that even though usually one of the reasons why people want to do message passing in atomistic context is to incorporate long-range information, we can show that it actually doesn't work. It works very, very poorly to incorporate long-range information. Here we are using a toy problem, which is basically the electrostatic interaction in a gas of charged atoms. And basically, there is, when you go from 1 to 2 to 3 neighbors centered on the same atom, yes, there is an improvement when you go from 1 to 2 because basically, if you look at the correlation between 2 neighbors, you get information also on atoms that are further apart than the cutoff. Okay? Imagine that I have a cutoff of 3 angstrom. Okay? If I look at 3 body correlations, I get indirectly information on the distance between these 2 atoms that is greater than 3 angstrom. Okay? So this is one way in which increasing the body order allows you to improve the accuracy for a given cutoff. But actually, going to higher body order or even using message passing doesn't improve the accuracy of the model almost at all. And I think that this is an interesting observation that, again, we can pinpoint very precisely on the message passing side because we are not changing the discretization, we are not changing the regression method. It's really just building in something that has the structure of a message passing step. Another very fundamental question that we can ask ourselves when we have these deconstructed models is what does it take to make a symmetric model complete? So with completeness here, I essentially mean injectivity. I want that if I have two structures that are different, they should be mapped to different points in feature space. And basically what I want to stress with this slide is that this is not only important for the two structures, because if two structures that are distinct in coordinate space are made to overlap, also the structures that are in their vicinity will become nearly degenerate. No? So this is the typical situation in which you can have corner cases that seem completely meaningless and not important in real life, but actually when you get something that doesn't converge for a corner case, very often it becomes numerically unstable for very reasonable cases. And this is one of these cases. If you force these two structures to, if these two structures have the same features because of a geometric degeneracy, because of the smoothness of the interpolation, also structures in the vicinity of those, even if they are not strictly degenerate, they will be very hard to tell apart, and it will be very hard for the model to predict the correct value of the energy of those structures. And so actually, mostly thanks to an amazing PhD student of mine, Sergei Pozniakov, over the past few years, we have been able to find that many of the descriptors that people had been using, and in many cases, myself included, thinking that they were probably injective and complete, they actually are not. We could build geometric constructions that up at least to the case of three neighbors, well, the structures become a little bit contrived. This is probably not a stable molecule, but you can build arrangements of points that are different, yet cannot be distinguished by essentially correlations between four atoms. And interestingly, we have also been able to show that a certain family of geometry decorated graph correlation network, graph neural network. Here we are showing results specifically for SNET, but there is a whole family of these that has the same issue, cannot distinguish pair of structures irrespective of the cutoff and irrespective of the number of message passes that you do, basically. And this means that you have structures that are different, have very different energy, but are predicted, SNET or any distance-only graph neural network will not be able to predict that the energies are different. And again, what I want to stress is that the work in classifying and in systematizing the construction of the model allows us to show these degeneracies not just for one model, but for a whole family of models. So this is one first way in which I think one can bring insights and interpretation and explainability into a model, so understanding what is the structure of a model. Another thing that you can do is what I call model introspection, which is basically using this understanding on the structure of a model to together with ablation studies or other types of numerical experiments to make some inference on the nature of the physical interactions within a system. So for example, I told you about locality and additivity, but how local is the structure property relationship in my system? So one thing that you can do very easily once you understand that your model is basically using correlation functions within a certain cutoff, and once you understand that your model has, in the complete basis set limit, has the potential of approximating any function of 2 or 3 or 4 atomic positions is basically just to build learning curves for different models with different cutoff distances. And what you see is that if you use a short-range cutoff, actually, for a small training set, the model works very well. It's very efficient. It's very information efficient, and this is because here I'm trying to predict the cohesive energy of some small organic molecules which are dominated by covalent bonding, and covalent bonds are typically within 2 angstrom. So if I have a small amount of data, 2 angstroms are enough to capture the covalent bond, and so I can actually build the most accurate model with a small amount of data. But now if I have more data, what happens is that I have no information to learn about hydrogen bonding and longer range interactions, and the accuracy of the model saturates. So I can go to a higher cutoff, and then you see that this delays the saturation, and so on and so forth. And so, in a way, building an envelope of these learning curves gives us a way of estimating how much energy information is contained into a region of 2, 2.5, or 3 angstrom around a given atom. Then, of course, once you have this insight, you can also use this insight to improve the model. And so what we did was to build multi-scale models in which we combine kernels or descriptors with different length scales weighted in a way that reflects the relative information of different energy contributions within a molecule. And by doing this, you get a model that basically does the best across training set size, because it knows that it has to focus first on the covalent bond, but then when information arrives, it can also start learning about non-bonded interactions and so on and so forth. Now, if I can come back to this problem of locality, so, does this mean that in order to learn any problem in chemistry and in condensed matter physics, I just need to progressively increase the cutoff? Well, unfortunately, this is not the case. Those of you who remember, all the pathological behavior of series that don't converge in absolute value, one fantastic real-life example of a series that doesn't converge in absolute value and leads to all sorts of painful situations is the problem of electrostatic interactions. If you take a ionic crystal and you try to compute the energy of this ionic crystal, you get a different result depending on whether you sum over spheres or over cubes of increasing size. And the fact that this basically never converges to the same value is an indication of the fact that you're not going to be able to solve this problem by just making the cutoff larger. And another way of looking at it is, you look at the cohesive energy curve of a charged molecular dimer, and it's basically not converged to 0 even at 50 or 100 angstrom. You will never be able to build a model with a cutoff of 100 angstrom. So, and of course, if your model is cutoffed, when the molecules are further apart than the cutoff, you can't predict that the energy changes at all. The molecules don't see each other anymore. So, our solution to this problem is basically to change the way we build the descriptors. As I anticipated, what we are doing is start with this field that describes the atom densities. This is not an actual electron density. This is just a sum of Gaussians. But then we solve the Poisson equation for this fictitious density. This gives us a different field, something which looks a little bit like an electrostatic potential. It's not an electrostatic potential. I have a different channel generated by the atoms of a different type. So this is not a potential, but it has the correct asymptotic behavior. And then we can build descriptors of this potential and we symmetrize them, we run exactly the same procedure as before, and this gives us these mixed descriptors that combine a descriptor of local structure with a descriptor of the long-range structure. And you can actually show, again, that if you build a linear model on top of these descriptors, you actually have exactly the same descriptive power of a multi-pole model of fixed charges. Okay? And I think that it's very nice to know that in a simple model limit, our descriptors map precisely on a very well-defined, physically rooted model. And then, of course, if you don't do linear regression, but you introduce nonlinearities, your model can do more. But at least you know that in a well-defined limit, it is rooted into something that has a well-defined descriptive power. So when I say that it can do more, it's because, for instance, we can also predict the asymptotic behavior of interactions between molecules that are not charged. And so this is a 1 over r to the 6. This shouldn't be describable with a multiple expansion model. But when you use a nonlinear model on top of these features, it does work. And we can also do something, I mean, again, this is perhaps getting a little bit too much into the details of the domain, but this is the interaction between a molecule and a metallic surface, and this involves polarization of the surface by the electric field generated by the molecule. So this is something that goes very far from a fixed point charge model, and still we can get a nice approximation of the asymptotic behavior of this interaction. So let me give you another example, which instead looks into the problem of chemical complexity. So I explained to you that basically the way we deal with the chemical nature of the atoms is by putting different densities depending on the nature of the atoms. The problem is that when you compute correlations of these densities, you also have to take outer products of the discrete channels that correspond to the densities. So if you basically have 10 elements and you look at 3 neighbor correlations, you have 1,000 channels corresponding to the correlations between the different types of atoms. So this clearly is something that can't scale up. And so the idea that we had here is basically to go back to Empedocles, and, or I mean, every culture had this, at a certain point, this notion of classical elements. And basically what we are doing is very, very similar to the idea of saying, okay, rather than learning the behavior of carbon, boron, and nitrogen, I will learn the behavior of a small number of chemical archetypes, fire, stone, water, and simultaneously learn the composition of the real elements on this basis of archetypal pseudo-elements. So basically this means that there is this matrix of alchemical weights that tell me what is the composition of carbon in terms of fire and water and stone. And so with this, we can take a very large sector of the periodic table, a bunch of transition metals that are relevant for high entropy alloys, and we do a compression. So basically we build models that as the first steps compress these 25 elements onto 2, 3, 4, 5 alchemical channels. And what we can see is that here I want you to focus in particular on the yellow, red, green, and blue line, that basically the accuracy of the model saturates at 4 pseudo-elements. So there is no reason of using more than 4 pseudo-elements in the description of this system. If you want to make your model more accurate, you shouldn't increase the number of pseudo-elements, but you should increase the correlation order of the density. Okay? And given that basically 3 and 4 are almost as accurate, you can also play the game. So now you have to imagine this means that there is involved into this a matrix of 25 times 3 components, which basically gives the composition of the 25 elements on these 3 components. So what can we do? We can plot these weights in 3 dimensions. And what is really nice is that these weights that have been learned by the model, by trying to get the most efficient compression, reflect the arrangement of the atoms in the periodic table. And this is not something that we have built into the model, it's something that has emerged from the learning exercise.
Well, can you interpret the PCA axes in some way? It's your primitive pseudo-elements, what do they represent?
Yeah, so we do a PCA because given the structure of the model is actually invariant to unitary rotations of that matrix. So to make it unique, we do the PCA because otherwise it can come up in every orientation. But of course, the first principal component is the most important one and but something which is also very interesting is that it's not linear, it's not just the periodic table. And this actually reflects the fact that actually the elements that are at the edges of the transition metal sector are more similar to each other in practical applications. And actually, if you look at the Wikipedia page of the periodic table, you will find that somebody has proposed an alternative visualization of the periodic table in which the transition metals have exactly this, this kind of a U shape. And another thing which I really find incredibly cute is that, okay, for good or bad reasons, we had decided not to do the full D block. We left a few elements out, the technetium because it's not stable, the others because they are almost never used in high entropy alloys, but it's kind of a pity that we don't have rhenium and osmium. And so what we tried to do was to say, well, why don't we just put rhenium and osmium in between tungsten and iridium? And actually, just by interpolating these weights, and then it's projected in three components, and then those three components, you can use them with the same weights without re-optimizing anything else. The model, I mean, it's not perfect, the accuracy decreases, but you can basically run simulations that contain rhenium and osmium and are very reasonable, even though we have never trained on something that contains rhenium and osmium. So to me, this is really interesting because it emphasizes that the notion of interpolation or extrapolation ability of a model really depends on the structure of the feature space in which you are interpolating or extrapolating. Okay? Here, from an absolute perspective, we are adding elements that the model has never seen. So how can you be more extrapolative than that? But the structure of the model means that this interpolation makes sense. Of course, I think that this is kind of anecdotal. I wouldn't draw too general conclusions, but I think it's very thought-provoking to see that we can do this, and the model is very reasonable, even just literally. So these are 1/3 iridium plus 2/3 tungsten. It's kind of interesting. So
I have a question.
Yeah.
But how do you interpret these pseudo elements? Do they correlate with anything like, I don't know, number of valence electrons?
I mean, in this case, they correlate with the number of the electrons, clearly, and the total number of electrons. And for some reason, it captures this, the fact that it's actually not a linear relationship between the number of valence electrons and the properties of the metals.
That's exactly what I was trying to ask. I mean, it doesn't correlate with some ionization energy or some such thing.
Well, yeah, it seems to suggest that the number of electrons per se is not the most important quantity, but there is some other quantity that summarizes the property of the atom. Mm-hmm. That is more important than the number of electrons.
No, we haven't systematically investigated this, but yeah, you're right. This would be an interesting question to look into. Yes, I agree. So in the last section, I want to take a little bit of a different perspective. Yeah, sure.
When you were discovering this, you were forming compounds, basically, right, from one of these atoms and what else?
Oh, you see, I have taken out a slide this morning. I shouldn't have. So this is really, really ambitious. We are basically making simulations with 25 elements all simultaneously together. So this is 25 elements interacting with each other in every possible way.
But the 25 elements are these, or is there something like an oxidizer, some kind of?
No. These are all transition metals. It's all only within these. Basically, what we are doing, the end goal here is to study the thermodynamics and the physical properties of high entropy alloys. So we are running simulations with up to 25 elements and seeing how they transform when you quench them, when you create a surface, and these kind of things. So in this last part, I want to take yet another perspective on how you can incorporate explanations into this atomistic modeling. And this has more to do with the sort of visualization, post-processing, and analysis of data sets. And so one thing that we are trying to do here, so one thing that I always found extremely frustrating is the fact, actually my first excursions into machine learning for atomistic modeling were with dimensionality reduction and the construction of unsupervised machine learning models. And something that has always frustrated me a lot is that when you do these things, then you typically say stuff like, okay, we do a unbiased data-driven analysis, and that's not true. Because every time you do this unsupervised analysis, you actually, you have so many parameters to play with in the definition of the descriptors, in the hyperparameters of the dimensionality reduction algorithm. I mean, t-SNE is there is a fantastic paper that shows that with t-SNE you can find anything in a data set by just playing with perplexity. And so, but in general, I always found that the notion that with an unsupervised machine learning model you can magically get unbiased insights is a bit disingenuous. And so something that we wanted to try to do is to mix in the simplest way possible, a supervised component into the dimensionality reduction. So we found this paper, actually, I am sorry, I took this out for another deck of slides. So this is the original method, the linear version. This PICOVAR is actually a 1992 paper by de Jong et al. And it's a very simple idea. Basically, it's a mixture of a PCA type loss and linear regression loss. So you mix a dimensionality, a linear projection, an orthogonal projection from your features to a latent space, and linear regression in the latent space. So basically, you try to find the latent space that that basically preserves the variance and allows you to linearly regress the targets. So what we did is basically just generalize these to kernel methods, which is relatively simple. And then what you get is a method with a single parameter that allows you to switch from linear regression, because, of course, if you only want to do linear regression, you can actually do that with a one-dimensional projection of your feature space. You project on the normalized weight vector, and then you can do as well as with the full features. And on the other end, you have PCA. And what you can see is that basically there is a pretty broad sweet spot in which you get pretty good regression capabilities while being able to preserve a large fraction of the variance. And we believe that this is a very useful way and very simple way of visualizing data. And as an example, here we are looking at the data set of hypothetical structures of carbon. What is interesting here is that we basically do just kernel PCA, and what I would have done a few years ago would have been to come here, show you this, and then start arguing, you see, here you see the diamond-like structures, here you have the graphite sheets, so you get insights into this data set by looking at this. But actually, I mean, they are all mixed up, really. No? And since I know already what I'm looking for, I can glance some insights, but it's not really in your face. So actually, what happens if you add as an explicit target the cohesive energy of the structures? So what happens is that actually, well, you get something that correlates very well with the cohesive energy of the structures, and at the same time, you get really much, much better clustering of the different types of bonding in carbon. So what I think is nice here is that I have added an explicit regression target, which is kind of obvious regression target, and this has also generated something that from the structural perspective is much more insightful, much better separating, and it's just a much better map of the behavior of carbon than something based exclusively on the descriptors and an unsupervised projection. And then, so we are now also trying to incorporate this into all sorts of problems. So, for example, here we have, it's kind of, we're a little bit silly, so the whole paper is played on a Harry Potter metaphor. We call the model the sorting hat because it sorts hypothetical zeolite frameworks in zeolite frameworks that can be synthesized with different compositions. But anyway, I think it's fair to be silly every now and then. And so basically we apply a lot of these techniques, including also this principal covariate regression. And the idea is then to be able to separate the structures that have the highest potential of being synthesized from the millions and millions of hypothetical frameworks that have been proposed by computational searches. And the idea basically is that we try to build a classifier that can classify the known synthesized frameworks and the non-synthesized frameworks, and those for which we misclassify, so the hypothetical frameworks that we misclassify as synthesizable are those that have the highest potential of being synthesized. I should say that what makes this very, very difficult from a data analysis perspective is the enormous class imbalance. So we have, you can easily find data sets with 1 billion hypothetical frameworks, and there are 250 zeolites that have been made. So there is a really huge imbalance, and this is why we actually have to play very, very careful with the complexity of the model and what we do. Another example of something that we... I think it's basically done. So one last application, and this is something actually from a excellent postdoc, ex-postdoc. She's now Rose Sersonsky. She's now an assistant professor at UW Madison. And so the idea here was to try and understand what are the factors that determine the stability of molecular crystals. So this is very important for pharmaceutical companies because it's not enough to have a molecule that is active against a disease. You also need to be able to bring it into your body, ideally orally, so it has to be soluble, and you have to have something that you can store on a shelf for more than 24 hours, so it should also be stable long term. And so the crystal structure that these molecules take is very important to determine bioavailability and shelf life. So there is a lot of interest in designing basically, once you have an active compound, you can mix it with other inert compounds so that they form co-crystals that are more soluble and or more with a longer shelf life. And so basically here the idea was to try and recognize what are the building blocks of a molecular crystal and how you can play with the building blocks to get a crystal with the properties that you like. And here again we do a big data analysis exercise, and we assign energies to the different groups with a regression exercise. So basically we try to learn the cohesive energies of the crystals and assign them to different subgroups. And then we build maps which correlate both with the structural diversity and with the cohesive energy of the crystal. And then basically there are these interactive, if you go to these small motifs.matcloud.xyz, you can navigate these maps and understand what are the groups that make a crystal stable and what are the groups that make a crystal unstable. I mean, it's a long paper, so I cannot describe you the details, but it's an interesting one. So I probably will skip these, but basically the main idea here was that something that we are trying to do right now, this is more future perspective. So what we are trying to do now is really try and make the mixing of physical-based and data-driven modeling as seamless as possible. So there are many opportunities of bringing very traditional physical concepts inside a machine learning model. And just a few examples. Here we were trying to predict the dielectric response of water. And when we did this for ice and water, so in the condensed phase, we found that the models were much, much, much worse than in the gas phase. And this actually has a very good reason, and the reason is that the dielectric response in the condensed phase is a collective effect. Basically, molecules are polarized by the field generated by the other molecules. And so what we did here was to map the collective response on an effective molecular response using a relationship from classical continuum electrostatics. Then we learn, and this is a very simple invertible relationship. It's not time-consuming to apply that. Then we learn this effective local response, which is much easier to learn. And when we make a prediction, we predict the simple properties and transform it into the collective property. And so this is one way in which knowing about the physical behavior makes machine learning much, much easier at no additional cost. Another example, when you want to learn dipole moments, it's very hard with these local moments to learn the polarization that comes from charge separation. And so what we did here was building a model that combines local dielectric polarization with the presence of charges that are geometrically separated and give rise to a dipole moment just by geometric separation. And I mean, the long story short is that you can get much better models that transfer much better to large molecules if you incorporate one part that is based on an explicit charge behavior. And so, yeah, really the idea is to deploy these as extensively as possible and stop really making a distinction between physics-based and data-driven techniques. And for example, one thing that you can do is to incorporate the behavior of excited electrons by learning the ground state energy and the density of electronic excitations. So you learn these that are ground state properties actually, and you combine them with an expression where you might recognize basically electronic entropy and the excitation energies. So this is a purely physics-based expression that is dirt cheap to apply and allows us to extend the reach of a data-driven model without doing any more machine learning. So I think there is a lot of potential just by using trivial physical expressions to make machine learning models more transferable. I mean, here we can simulate hydrogen at 50,000 Kelvin. And yeah, something that we are starting to do, but I have really nothing to show, is also incorporating experimental data in all of this. This is something which I really think is going to be very important. And the reason why this is not entirely a triviality is that I think that the real benefit would be to use machine learning to mix theoretical and experimental predictions, because you are really in a situation in which you have few experiments that are the ultimate truth, and theoretical predictions that are usually cheaper to generate, but they are not true. And so, yeah, if you want to try any of these, we have a lot of code in different states of polish. Given that this is mostly about interpretation, visualization is a big part of interpretation. And so we also have an online tool to visualize chemical data sets. And with these, I will just conclude. Thank everybody for listening. And if you have any questions left, we can Answer now or during the break. Thank you.